Hi, my name is Nafiz Rahman. In today's episode, we'll be looking at open channel flows and the various characteristics behind them. A question that I should probably answer first is what is an open channel flow? An open channel flow is when a fluid, or in this case water, interacts in the specific scenario. So as you can see, we have an upstream gate and we have a downstream gate. The upstream gate closes by going down, meaning we'll have a small opening at the bottom. And on the complete opposite side, we have the downstream gate, which closes by going upwards, meaning we'll have a small opening at the top of the system. Some things I'd like to note is that the depth gauges, even though the system is at an angle, still maintain the idea that they are in balance with the world. Something that is very important that should be of note is the hydraulic jump. As you can see in this experiment, we'll essentially get three different slopes. We'll get slope S naught, which is basically the slope of the system, and it is stationary regardless of what happens. We have S2, which is the water coming from the upstream gate down the system, and this is how you would basically expect water to react by going down any slope. But we now have S1, and you can see that it has an increasing slope, and happens because of a hydraulic jump. So as we'll see in a hydraulic jump, what essentially happens is that we have the downstream gate right here. So all the water that comes over here essentially gets pushed uh, backwards and pushes it to the top, meaning the water comes over here and it'll want to leave that circular water flow and go to the top, and this will continue to happen. This is pretty much very important. Looking at the specific slopes, we can see how the depth changes. As we go along the x-axis, we see that for, in this case, S naught, the depth increases of the water. And this makes a lot of sense because S naught is a decreasing slope, which, as our experiment saws, does line up with the theoretical assumptions. Looking at S1, we see that the slope also increases as it goes on. This makes sense because due to the hydraulic jump, more water is being added into the system, making the depth increase as it goes on. This again lines up with the theoretical values as we've seen with our experiment. S2 is a little bit more interesting. We see that the depth actually decreases and then levels out. This makes sense. When we look at the upstream gate, we open it up and a lot of water will flow through. And when this happens, it begins to level out as it flows along the x-axis. And so that's why what we see inside of our experiment does line up with the experimental. Let's look back at our previous graphs. As we can see in both of these graphs, we see a solid black line. This is our theoretical value. We get our theoretical value based on the equation at the bottom of the screen. The only issue is, in order to get the theoretical value for this specific experiment, we need to calibrate it. This is where the first y value comes in. And because we use the same y values for the theoretical and experimental, they're the same, and it's very correct. The only issue is every other value becomes very sensitive to this y1 value. Which is why if we were to do this experiment again, I would change it up so that this formula would include other characteristics such as friction that we face inside of the experiment but not inside the theoretical.